I'm going to kick things off with a riddle for you all. What does this coin, Antarctica, and a piece of John Deere equipment have in common? We'll come back to that. Unless somebody has the answer now. But So I lead John Deere Labs, which is our San Francisco-based innovation office for John Deere, and I lead sustainability. Now, those might seem like two very different things, but over the next 17 minutes, hopefully you'll see that they're very much interconnected. So first, how do we look at sustainability? Well, we really look at it through the lens of sustainable outcomes for our customers who are producers, for the communities they're in, and for the consumers down the line that are using their products. And at a very practical level out on the field, it means sustainable water use, better air quality, reduced input use, and farming practices that support better soil health. However, at the end of the day, this all has to add up to one thing, and that's financial sustainability. Because we're acutely aware, if you don't have a financially viable and sustainable operation, none of the other things matter, because you're not going to be around next season to farm. Now, fortunately, in agriculture, these are not opposing forces. In fact, they're very much complementary, because it all comes down to one thing, and that's doing more with less. And at John Deere, if we have even a small opportunity to change that equation for the producer, it can have a very large impact. And that's because we're global. We have customers in over 100 countries. Do you know what portion of arable land has a piece of John Deere technology on it? 25%. So when we've heard all of these statistics and projections that we need to feed 9.7 billion people by 2050, and that we need to increase food production by 50%, we recognize we're not going to do that by farming on more land, because we just don't have it. And that's where we have a responsibility to give our customers, our producers, the ability to leverage the technology to feed that growing population. Now, today, I'll be talking primarily about broadacre crops, but these principles and these technologies apply in other crops as well, in dairy and livestock, which is big in New Zealand, as is forestry, and in fiber production as well. So let me show you how we do that. Now, first, it's important to recognize we really think of this as a production system, and it really is a system, because while each step is critically important, it's really the sum of the parts. You can't optimize one but not the other. So the technology and innovation has to span everything from preparing a field for planting to making sure that every seed planted counts, that every drop of fertilizer, herbicide, fungicide counts, and that when it comes time to harvest, every grain is able to be harvested off of that field. And while the pieces of equipment on the slide are green, because obviously I work at John Deere, this is very much an evolution that's taking place in agriculture. Thousands of years ago, we started with pure muscle. First our own, then domesticating animals. Then we really started making progress over the last 150 years through mechanization. Tractors came around. Genetics started improving. Chemicals started improving. But really, we're just at the beginning right now of the digital and artificial intelligence revolution, which will help us farm smarter, reduce costs, reduce time, and increase yields. So while we've historically looked at really improving that mechanical model, growing the horsepower of our equipment, growing the size of our equipment, looking ahead, and the next frontier I'm focused on is really how do we make things more automated? How do we make things more precise? And how do we really start farming at the plant level? And all of this has to happen repeatedly between seasons, between continents, because you can't just do it once. This has to be something that happens over time and over all geographies. So let's start with the first step, and that's preparing the field for planting. And this is really important because it sets the foundation and bedrock for a seed and its survival rate. 26 to 40% of crops globally fail because of weeds. And so what we would do in the past is we would broadcast the ply through this 120-foot boom herbicide on the field to get rid of the weeds. It would apply up to 225 gallons a minute of herbicide. But we can do better than that. And that's because this isn't one monolithic application that's happening. This is 97 different individual nozzles that are turning off and on. And they're doing that 30 times a second. So now we have these individual controls, which can really start making things interesting, because as we go through the field, those nozzles don't all have to be going at the same time. They can be modulating how much they're putting on the field. So when we're going through a waterway, for example, we can shut off those nozzles and not apply herbicide where it doesn't need to happen. Those of us that remember basic physics recognize that when you're making a turn, one side goes twice as fast as the other. And that means it's really easy to over-apply chemical, but not with these robotic systems. And so now we start really having both financial and environmental benefits. These technologies reduce herbicide use between 2 and 5%, which is great, but can't we get more precise than that? Well, we can, and we should, and so the way we do that is we start targeting at individual weeds. We can put 36 cameras on these booms. We combine that with artificial intelligence, machine learning models, and these precise nozzles can now reduce herbicide use by 77%. Now, it's not just that financial and environmental benefit, but weed resistance to herbicides is a big problem globally. So when you stop applying broadcast spraying herbicide, you can now target those weeds with specific formulations so that you can make sure that that weed is eliminated. Now, this might seem straightforward, but it's not easy. These booms are traveling at 19 kilometers per hour. So you have milliseconds to be making these decisions, 50 milliseconds to be precise. So you have to collect all this data from these cameras. You have to integrate it with 400 other sensors on this piece of equipment. Everything from wind speed to boom orientation, because this isn't like driving down a freeway. And you have 100 computers talking to each other. And they need to do all of that within 50 milliseconds. And that's just the preparation phase. We haven't even gotten to planting the seed in the ground. And when we do get there, accuracy is even more important, because to give each seed the best chance of survival, it has to be planted at the right depth, at the right place, and at the right time. And it has to be done repeatedly, billions of times. Now, billions is not an exaggeration here, because a typical farm in the US Midwest of 2,000 hectares, I know that's small by station standards in New Zealand, but in the US, that is the equivalent of having 750 million plants in one operation. A single field of corn, such as one here, can have up to 8 million plants. And so this is where our coin comes back, because in order to get this level of precision, our equipment has to navigate to within the width of this coin. So this is 23 millimeters, which is pretty close to the 25 millimeters of accuracy that our equipment is able to navigate to. So you have multi-ton pieces of equipment that are able to drive themselves with this accuracy. And that really starts getting interesting, because now you're able to plant, as you can see here, plants right at the exact same spot that they need to go. And you're actually able to do it faster than a human, because a human can't actually drive with that accuracy at those speeds and be able to make those decisions. And that's important because it's all about time. Planting windows are really short. You only have a few days to get your crop in the ground before you might be jeopardizing the crop's viability down the line. And again, this isn't easy. Not only do you have to have hundreds of sensors and hundreds of controllers, but when you're planting 150 seeds a second with each control unit, you're doing so in very harsh environments. There's dust, there's rain, there's mud, and this has to be done reliably in conditions that break axles on multi-ton pieces of equipment. Now, who's been in a combine before? Who's driven a combine? Anybody? So there's a few hands here. But this is a 10-ton piece of equipment with 20,000 moving parts. And you're trying to drive this thing straight, because every time you stray over a little bit, you start losing a few percentage points in terms of productivity and losses. And this is also a time-sensitive operation, because like planting, you only have a few days before the weather might come in and your crop might be ruined. So productivity is key. And by the way, while you're driving this massive piece of equipment, you have a little grain window that you're looking through in the back to see what's going on in the back of that grain tank. Because you're trying to make sure that every grain is harvested as best as possible. You want to make sure there's no broken kernels in there, and there isn't too much trash coming from plant matter. So you think texting and driving is bad? This is really tough. And these half a dozen settings that you're adjusting depend on everything from the humidity in the air to the slope of the ground that you're driving on. So naturally, we want to make this easier for producers. We do it with computers again. So we've already talked about the navigation piece that helps us navigate to within the distance of that coin. But now, again, we bring in sensors, we bring in artificial intelligence models, and now, when it all comes together, this equipment can drive and collect 100 tons of grain per hour with less than 1% loss. And it gets even more powerful because all of these pieces of equipment are connected together. John Deere alone has 220,000 pieces of connected equipment. And remember how I said it's all about time? Well, wouldn't you like to have two planters in the field talking to each other and not planting over each other? Well, that can happen today. In harvest, you never want this factory on wheels to stop. You want it to keep going and never stop. And so what you do is, if you thought that was too easy, now you have another multi-ton piece of equipment driving next to it with a grain cart in the back, and you are now filling that grain cart. And by the way, don't spill any of that grain, because all that hard work that you did, now you'll just be dumping it right back on the ground where you have to pick it up again. This precision technology combined with the connectivity actually enables you to have those two pieces of equipment talk to each other and drive next to each other on their own. So this is happening today, is you just pull up and they're able to synchronize and off you go. Now, this is all great, but can't you even take that further and actually learn from each pass? So now you have a situation where the planter can inform the sprayer what it planted. And you can take that even further, because you can take that information, combine it with satellite imagery, and now the combine can actually know what's on the other side of that hill and predict the biomass that's there and really have some form of adaptive cruise control. And this exists today. This is not science fiction. So when you're approaching that hill, the equipment can slow down. It can change its settings because it knows exactly what's happening on the other side of the hill. So by now, hopefully you're recognizing that it's not just about iron. It's about technology as well. So how do you make this happen? Well, this is where our coin comes back, because to get this level of precision, we need to have a global network of GPS reference stations, including in Antarctica, in Peru, on islands in the middle of the ocean, and that lets you navigate multi-ton pieces of equipment to within 25 millimeters. But it's not just the hardware. You need to have the data infrastructure to support this as well. A lot of our customers choose to store their data in the cloud so that they can access it in mobile devices, on web, as well as in their equipment. And that's a lot of data. Our equipment generates between 10 and 15 million data points a second. In the time that we've been on the slide, it's uploaded 2 terabytes of information to the cloud. And this really starts enabling some really interesting things. To give you a little bit more of a perspective here, just in the last 12 months, our customers have documented their practices on 95 million hectares. That's mapping New Zealand north to south 4 times. And all of that has to be supported by our cloud. And when you take this massive amount of data, this billion map layers, you now are really putting the power of this technology in the hands of our growers and enabling our equipment to make better execution decisions in the field. Your soil map can inform how you plant. Once you know what's planted, you can inform how best to fertilize that field and that crop. And at the end of it all, when it comes time to harvest, you know exactly how well you did in the field. And that helps you optimize for the future. So the next time you look at a piece of equipment, you're probably looking at it a little bit differently. Because all of these innovations come together to make every seed count, every drop count, and every grain count. And that enables sustainable outcomes for our farmers. This enables them to do more with less. And that helps them be more profitable and sustainable. And that is why this technology innovation hat that I wear is interwoven with a sustainability hat as well. Thank you very much.